all, I want to define a little bit what I mean when I talk about dwarf galaxies. So for my definition, everything which is fainter than the LMC is a dwarf galaxy, which includes the dwarf elliptical galaxies, which we heard before, like the Fornax dwarf galaxy here, a satellite of the Milky Way, but also dwarf irregulars like the WLM. So these here are all dwarf galaxy satellites of the Milky Way. So they range from 1 billion stars in solar masses, in the baryonic mass, up to these things here, which only have a few hundreds or a few thousand stars. So everything I throw into the same bucket as dwarf galaxy. However, what is not really well represented here is the actual sizes. So if we fix that, we also see they span a huge range in stellar mass and a huge range in sizes. So this thing here could also be called a Hobbit galaxy, not just a dwarf galaxy. So anyway, almost 50 years ago, Donald Lindenbell discovered a peculiar arrangement of the dwarf galaxies around our own Milky Way. Here, this is a map, an all-sky map of our surrounding, and indicated here, I screwed up with the colors, but indicated here in magenta, magenta red, okay, that's almost the same, are the dwarf galaxies. And what we see is that they almost lie on a circle. And if they are on a circle, this means that they are in a planar arrangement. Also, the globular clusters, some of the globular clusters back in that time also followed this, this peculiar arrangement of this planar structure of dwarf galaxies. So Lindenbell thought that, okay, this thing here, that's the LMC and the SMC, fell in, got disrupted, and all these dwarf galaxies here are basically on the tail of the LMC. So the LMC was shredded and it formed these nice satellite galaxies from the infall of the dwarf galaxies. So that was 50 years ago. At that time, we knew roughly 5 or 6 dwarf galaxies. And you see that from, let's say, beginning of modern astronomy till now, or till 20 years ago, the number of the dwarf galaxies around our own Milky Way stayed really low. And of course, because this is a survey conference, I guess you know what happened here. I already spoiled this. So thanks to SDSS and DES and other surveys, this number exploded. So we have today a much better handle on studying this distribution of satellites around our own Milky Way. So what happens when we add these dwarf galaxies also to the picture, which was published 50 years ago? So here's another view. If we take an observer outside of the Milky Way, this is this planar structure which was found before, and all the crosses are the dwarf galaxies known today, or 5 years ago. So I guess that's only half of the ones we know today. But still, what you see is that the dwarf galaxies still seem to be arranged in this planar structure. This is an edge-on view of this plane, but let's go to a face-on view. Thanks to observations, proper motion observations with the Hubble Space Telescope and Gaia and the combination of these two, we have quite a good idea about their orbits within this planar structure. And what we see here, so here these are the orbits, and what we see is that they seem to be co-rotating. So almost all of them, which are here in the plane, they seem to be rotating in the same direction, except this one here, which goes into the other direction. Let us make a thought experiment and think about a perfectly aligned planar structure. So we here have the Milky Way, and everything is perfectly aligned in a super flat plane, like, I don't know, the planets around the sun. Oh, that's not really perfectly flat, but yeah, perfectly flat plane. So if we look at the scatter of the orbits, the normal angles, the scatter would be basically 0. However, if we now think about this, this planar structure has some kind of a thickness. And now we say, okay, this dwarf galaxy here is orbiting within the least possible orbit to be still consistent within this planar structure and be gravitationally bound. Then its orbit would look like this. We have another dwarf galaxy with this orbit, so the normal angle would be like that. And we can do that for all dwarf galaxies. And we get a measurement on the scatter of the orbital poles. So we can measure that, and we can rank it from the smallest scatter of a dwarf galaxy to the higher ones, and can show here. So we can do that theoretically just from the prediction of their positions within this planar structure. That would be this magenta line, and this is this region here is the, if you take into account the uncertainties, and the green line here is the actual observations. So if we then measure the orbits, and we see that within the uncertainties, the scatter or these normals, they are really almost perfectly aligned with this planar structure. So it really looks like these planes or these dwarf galaxies co-rotate within this planar structure around the Milky Way. Another view on how to look at this, what I always like is to look in history. So if you are here on the left panel, we look at the history of the observations. So we are going back in time from 2008 till today. On the y-axis is the errors. On the right panel, we have again history of observations, and here's this measure of this orbital, of the scatter of the orbital poles. And what we see is that the better the observations became, the lower the scatter went down. So with each better observation we have on these orbits, it looks like these satellites are constrained more and more to this plane of satellite. This hasn't not just been found for the Milky Way, but for the Andromeda galaxy, which is our neighboring galaxy. There seems to be also some kind of planar structure here, which seems edge on. And if we look into the motion of the dwarf galaxies within this plane, we see that on the one side, it looks redshifted, and on the other side, it looks blue shifted. So if we think about this, that around the Andromeda, there's also this planar structure, and within that, the dwarf galaxies seem to co-rotate. We would assume that if it's doing something like this, on the one side, it's moving towards us, so the light is getting blue shifted. On the other side, they're moving away from us, and it looks like it's redshifted. So we exactly see the same picture here. Now you can, of course, say that's just 2D, that's just line of sight measurements. But fortunately for two dwarf galaxies, there is now proper motion measurements, and it also seems that these are aligned with the planar structure. So for the two best studied systems, we both see that there seems to be some kind of co-rotating plane of satellites, dwarf galaxy satellites. Why do we care about this? Now let's talk cosmology. So here's the Millennium 2 simulation, which is a dark matter only cosmological simulation. We feed in Big Bang and gravity models and everything and let it run to our point in time. And what we see when we look into, let's say, the knots of this cosmic web, we see the galaxy clusters and galaxy groups. Here, that can represent a galaxy group. And in the center, there's a Milky Way-like galaxy. And all these dots here, those are the dwarf galaxies. So what do we see? We see that it's actually quite isotropically distributed, not perfectly. It's not perfectly round, but it's quite isotropically distributed. And if we look into the motion, so if we look at a video, for example, didn't dare to put that in here with a PDF, but so you have to just trust me that the motions of these subhalos, they are quite chaotic, so they move randomly. So our prediction is that this is chaos, this is madness. But actually what we observe is that they seem to be dancing around their central object. So this begs, of course, the question, is the local group unique? Because I mean, that seems to be quite at odds from our cosmological models. So is the local group unique? We asked that and we can go to the next galaxy group, the Centaurus group. So we did a survey there. That was our footprint. We followed up the dwarf galaxies there, got their distances, got their velocities. And what you see here is the distribution of the dwarf galaxies. Here's Sene, and you also see some kind of planar structure, which seems to be edge on. And on the one side, it's blue shifted. On the other side, it's red shifted. So again, Sene looks like it's some kind of co-rotating as well. So the satellite's there. If you compare that again to cosmological simulation, so you measure, here we do that quantitatively, we measure the thickness, so we measure the B/A ratio. We measure this, so that's the thickness here. We measure how many satellites are blue shifted here and red shifted there, and compare that to galaxy groups in here, this time in Illustris instead of Millennium. We see that Sene is a 0.5% outlier, which is the same number as what we find for Andromeda and the Milky Way. So third best studied system, again, an outlier from our cosmological models. That begs, of course, the question, so is the local group plus Sene unique? Let's go to the next group. Here is NGC 253, so the sculpture group, and also recently there, David Martinez Delgado et al. Here's sculpture, found some planar alignment of the dwarf galaxies. And if you look here at the velocities, it seems that there's some overabundance of blue shifted dwarf galaxies there. Problem is that this part is not really well populated, which is why we just conducted a survey with the VST to search for more dwarf galaxies there. But this is still an indication that, again, there, the next galaxy group where we have data, it looks like there's some kind of planar structure. So it begs the question, is the local group plus the Sene group plus NGC 253 unique? Paper by Paudel et al. At NGC 2750. They also seem to see some kind of co-rotation, red shifted here, blue shifted there. So again, I guess you get the gist of it. Again, it looks like there seems to be some co-rotation, which seems to be at odds with cosmology. Do you see where this is going? So, yeah. Sorry? M81, interesting thing, I have a paper, paper ready for that. There is a planar structure. It is the first object where we actually don't see some co-rotating. So there seems to be a planar structure, but there doesn't seem to be some co-rotation. However, we just have the velocity measurement on the dwarf irregulars and not the dwarf ellipticals. So it could be that we see something on the first infall. So for that, the data is bad. So probably we are comparing apples to pineapples or something like that. So we have to be careful there. But yeah, we're coming soon. So, but the problem here was that we always looked on individual systems, which is kind of bad if we want to do statistics. So here's a survey, the MATLAS survey. It observed 260 early type galaxies between 10 to 50 megaparsec. So in this survey, there were only over 2,000 dwarf galaxies discovered. And Nick Jesus is also here, and he will talk about that later. Studied the distribution of the dwarf galaxies in this survey. I'm just skimming through. I don't want to spoil his talk, but I just show some examples and basically raise the question of, is this unique? I don't know. I don't know what to say currently. There are many different scenarios, but none of them within cosmology seems to explain this this planar structure. And we have now, going from, let's say, 50 years ago, we only had one oddity. We are now at, I don't know, many of these galaxy groups which are at odds with cosmology. And yeah, the question is now, what should we do with that? What does that mean for our standard model of cosmology? And with that, thank you very much for your attention.